Hello everyone. My name is Brendan Eagan. I'm from the Epistemic Analytics Lab at the University of Wisconsin-Madison. And I'm really happy to be talking to you today about a paper that Jace Brohinsky, Jingyi Wang, and David Williamson Schaefer and I wrote called Testing the Reliability of Inter-Rater Reliability. And the main theme of our paper is, hold on one second, is agreement, which in our field is most commonly measured with inter-rater reliability statistics such as Cohen's kappa, precision, recall, etc. And the goal with statistics such as kappa is to see if the coding of two or more raters on a sample or subset of data has agreement above some certain minimum value or threshold. And we want to know whether or not that agreement can generalize to the rest of the data set, a larger data set or a larger population. And in the context of learning analytics, this comes into play anytime two human raters or a human and computational rater establish coding agreement on any learning related data. And you'll remember that we generally control for making errors in this type of inference or generalization using p-values. And in the case of agreement or inter-rater reliability, we want to know if the agreement between the coding of two raters on a subsample of data would generalize to their coding agreement on the rest of their data. Unfortunately, previous meta-analyses have found that researchers simply assume that this agreement measured in the sample, the red area here, generalizes to the rest of the data set, the black area, without using any tests of generalization. That is, researchers are not controlling for type 1 errors when using inter-rater reliability. So let's unpack what researchers generally do instead. So first, researchers start with a code or they develop a code, and so they have a conceptual definition of that code. And then a rater codes some set of the data based on that definition. This creates a coded test set, which is then, sorry, got a little distracted by the chat there. This will create a coded test set, which is then provided to a second rater who then codes a test set independently, and then inter-rater reliability is calculated between the two raters of between the ratings of those two raters. And if that kappa is above some minimum value of interest, or the kappa is good, the inter-rater reliability process can stop, and then the two raters can independently code the data, or one of the raters continue on by themselves, assuming that the coding is reliable. But for those of you who've done this process before, you often know that the first time, usually we don't get the kappa that we're looking for. So the raters have to resolve differences, which can involve training the second rater. The second rater might want to change their coding, or this could involve a human tuning an algorithm. And sometimes the first rater also changes their coding or realizes that they need to refine their conceptual definition. And then this process continues, or this iteration continues until a significant level or a high enough level of agreement is achieved. And we refer to this approach as the common method. And as in the meta-analysis that I mentioned earlier, we looked at a number of different journals, but I'm just going to highlight a couple here. Looking at the Journal of Learning Sciences and the International Journal of Computer-Supported Collaborative Learning, we found 44 articles that used kappa. They calculated 141 values, but they tested for the generalizability of kappa 0 times. So they were all of these articles used the common method. The same thing was, almost exactly the same thing was true for the Journal of Educational Data Mining and the Journal of Learning Analytics. So what we wanted to see was, well, what does it mean for something to be good following the common method? Is this a problem? We think that there could be statistical errors happening here, but we need to figure out a way to figure out if that is a problem or how much of a problem that is. So to test the statistical approach of the common method, we conducted Monte Carlo studies. And now when I started to look into Monte Carlo studies, I thought, sweet, I can do this. This is going to be fun and exciting. But in reality, there were no roulette tables, there were no martinis. The basic idea of a Monte Carlo study is that you create simulated data sets, and in our case, ones that model the coding done by two raters over a large amount of data. And then we measure whether or not the agreement over this whole set, in this case using kappa, is greater than some threshold of interest. And a very common threshold for kappa is 0.65. Or on the other hand, it could be less than the threshold. And this represents the true kappa for this overall simulated set. We then take a random sample or test set from the data and calculate kappa on that test set. And in this case, the test set kappa is actually greater than the threshold that we're interested in when the true kappa is less than the threshold. And this discrepancy leads to a type 1 error because the test set is telling us that our agreement is okay when in fact it is not. But we don't do this just one time, we do this thousands and thousands of times, which allows us to generate an empirical or compute an empirical type 1 error rate, meaning for all the simulated sets with kappas below the threshold, we can measure how often this is happening, that the test set leads us to believe we're above our threshold in error. So in previous work, we've simulated the performance of the common method using Cohen's kappa, looking at a range of test set sizes or test set lengths that includes and exceeds what is typically used for establishing inter-rater reliability. And we did this in combination with a range of base rates. And a base rate of a code is basically its frequency. So a base rate of 0.1 means the code occurs in 1 in 10 lines of a data set. This is also referred to as frequency or prevalence if you're familiar with those terms. And we found that the common method has very high type 1 error rates, and in many cases, many times higher than the acceptable rate. And we can also see that this problem is worse for codes with lower base rates. And I see some chats. I'm just going to double check because I can't quite see them here. Oh, looks like a previous thing. So I'll just keep going. Sorry about that. So I was saying that this problem is worse for lower base rate codes. And it's not actually until we consider codes with a base rate of 0.2, meaning that the code is appearing in 1 in every 5 lines of data, and test set lengths of 800, that we get acceptable type 1 error rates. So these results led us to conduct analyses that are related to the results of the paper that I'm happy to talk to you about today. And we wanted to know if were these results specific to kappa, or do they persist across other inter-rater reliability metrics and across different IRR thresholds? You might have different inter-rater reliability thresholds depending on what your study is interested in. So it turns out they do. These problems do persist. So these are the type 1 error rates for % positive agreement. This is what they look like for recall. This is what they look like for precision. This is what it looks like for the F statistic. So we wanted to dig into this more, which brings me to the results from the paper that I'm presenting on. So as part of this exploration, we wanted to look and see if this issue was affected by different threshold levels. So here we're looking at the type 1 errors associated with the F statistic at 3 different thresholds for codes with a base rate of 0.5. And again, we see that while increasing the threshold helps with this problem, it's still a challenge. So this is looking at codes with a base rate of 0.05. Here's the same thing, but for codes with a base rate of 0.1. Again, it gets a little bit better, but still it's quite problematic, and especially depending on the threshold that you're interested in. Here we're looking at multiple commonly used IRR metrics with the same threshold. And the main takeaway from all of these tables is that while there's some variation, these problems persist across metrics and across thresholds. So these widespread issues with the common method illustrate that we need to solve these problems. But fortunately, they also outline a solution space that we can use to define a way to kind of deal with these statistical issues. So we kind of outline the solution space as we're looking for something that can work across these different inter-rater reliability metrics. We also want this approach to have acceptable type 1 error rates. We want this to perform well for low base rate codes because we've seen that that's challenging regardless of what approach that we're taking. And we also want this to be compatible with a method for determining appropriate and therefore variable thresholds, different inter-rater reliability thresholds. So the solution that I'm excited to talk to you about today is a statistic called Rho. And we have a little mascot for our statistic to make him a little bit more memorable. He's got a Greek letter Rho on his stomach. And I'm going to go through a little bit about how Rho actually functions today so you can get a sense of what we're proposing as one potential solution. So to start off, when we're calculating Rho, we generate a simulated set just like we did in our Monte Carlo study. But in this case, we're guaranteeing that the kappa or whatever the IRR metric of that set is less than our threshold of interest. And we don't do that once, we do that hundreds of times. And then we take samples from all of these simulated sets. and we calculate an iterator reliability statistic, in this case kappa, on all of these on all these test sets, which creates a distribution of kappas from test sets that come from larger simulated sets with poor agreement. And basically what that's doing is creating a distribution of kappa underneath the null hypothesis that our agreement is coming from a larger data set that doesn't have good agreement. And we can compare our observed kappa to this distribution. And if our observed kappa is greater than 95% of this distribution, we can reject the null hypothesis and conclude that our kappa must have come from a different distribution that had good agreement. Basically what Rho is doing is providing an estimate of the type 1 error rate for generalizing from a test set. And it functions similar to a p-value. Another way you can think about it is Rho is telling you when you've coded enough as a human, either between 2 human raters or between a human and a computer, when you're trying to minimize the amount that the human has to do. So if we think back to the common method loop here, we can see that this new Rho method adds 2 new crucial pieces. The first is that we create base rate inflated test sets, or use something called case control sampling, which I'll get back to in a moment. But the second is that when we calculate our iterator reliability statistic, we also want to calculate a Rho. And so if we get an iterator reliability statistic, in this case kappa, above our threshold and our Rho is below 0.05, then we can say that we're good enough to stop and let the 2 raters code independently, or have 1 rater code independently. So we ran a Monte Carlo study to check the performance of using Rho, and these are the type 1 error rates of using Rho with kappa, using the base rate inflation that I mentioned before. And I want to talk to you a little bit more about the base rate inflation step, because I think it's a crucial one, and it contributes to why we see these good type 1 error rates. So we're going to dive a little bit more deeply into this step in the process. So if you're interested, when we're in questions, I can go into a little bit more of the math of base rate inflated sets and the mechanisms involved, but for now I want to explain what it's doing generally and why it's useful. So if you remember, the base rate is just another way of saying a code's frequency. So if we think about the base rate of a test set, we run into an issue when base rates are low. When a code is very rare, it is more likely that your test set won't have very many of them. And this means that if you're trying to establish agreement, say for something as simple as which things are green, if you're looking at items, but you never actually see any green items in the test set, you're not actually learning about agreement on what, you're only learning about agreement on what's not green, if you never see any positive instances of it. So in other words, iterator reliability tests get less sensitive when the code base rate gets lower. They don't work as well. So iterator reliability metrics have sensitivity when the tests have more equal distribution of positive and negative instances of the code. So if I'm actually seeing some green things and not green things, then I can get more information about whether or not 2 raters have agreement. So using Rho allows us to test for generalizability of IRR for very low or even very high base rate codes by being compatible with base rate inflation of test sets. That is, instead of seeing 1 example out of 100, we could see at least 2 in 10. And as a result, Rho lets you work where IRR metrics are generally not as sensitive. By allowing researchers to work in a range of base rates where IRR tests are more sensitive, using this base rate inflation also gets you more information from each test set. So it's not common to reach high enough agreement with the first test set. So when you have extremely high or low base rates, you're not getting as much information as you do from false positives and false negatives unless you use this approach. And another thing to point out here is when we have good type 1 error like we see here, then we get to start being concerned about type 2 error rates or issues of power. So here are the type 2 error rates of using Rho with kappa. And what we're normally looking for is for type 2 error rates of 0.2 or lower, which gives us a power of 0.8. But it actually, the way that the math works out, we actually are recommending working with test set sizes around 40 if you're interested in a kappa threshold of 0.65, because it's better to take 2 shots at a power of 0.7 than taking 1 shot at a power of 0.8 with 80 items in your test set. I also mentioned before that we wanted this approach to be useful at different thresholds. And in our lab, a lot of our quantitative ethnographers in our lab were not really satisfied with the quality or the face validity of using a kappa threshold of 0.65. So they opted to use a higher threshold of kappas of 0.9 or higher. And this is the type 1 error rates and type 2 error rates of using a kappa threshold of 0.9. And here we can still see we're getting still much smaller much smaller test set sizes, even using this approach, where we're seeing that you need to use something around 80 to 100 in your test set to establish iterator reliability with kappa. In addition to using this with kappa and multiple thresholds, we've also used the same approach using the F measure, where we can generate a simulated data set that has an F measure below a certain threshold of interest. Again, we do this hundreds of times. We sample and we use base rate inflation in the sampling to ensure that we have a certain higher base rate in the sample that we're providing to the second rater. We then calculate our F measure, and again, this creates a distribution. These aren't the actual distributions of kappa and F. I'm just using them to illustrate that these distributions are non-normal, so we have to use an empirical approach. So this is actually all based on this initial set of being able to simulate a data set that has agreement underneath a certain level. And this is a non-trivial task and requires working out a good deal of math on the back end to ensure that we're going to get sets that have these properties. So we're interested in not being able to use rho for just kappa or just F measure. So we're working on a brute force method to create a null hypothesis distribution for any IRR metric at any threshold that you're interested in. And I'm not going to walk through the whole process again, but it's basically the same logic. So just to kind of wrap things up here, we have, I've just given you kind of an overview of how rho works and that we think it's a solution to these issues that we found with the common method. We also have an R package that we call ROAR that you can find. We also, if you go to the Epistemic Analytics website, we have an online version where you can just copy and paste like 2 columns of data from 2 raters in, and it will calculate kappa and rho for you. It's also built into our automated coding tool, Encoder. And just to kind of wrap things up, the common method we've seen is just as problematic with other iterator reliability metrics. We're developing and testing rho with the F measure, so we're trying to conduct Monte Carlo studies to make sure that the performance is good with these other metrics. And finally, as I just mentioned, we're exploring brute force approach so that rho could be used with any binary IRR metric. Thank you. I'll stop